Thank you, Jeremy, for this kind introduction. Before beginning this presentation, I would like to add something to the bio. I'm working for the Operation System Architecture in Department of Thales Avionics, but I'm also part of a multidisciplinary team in the laboratory called HEAL, which stands for Human Engineering for Aerospace Laboratory. And we are united around HEAL to share our vision for collaborative avionics in the aspect of future virtual assistant. This particular presentation will be held on the topic of study of knowledge exchange for airborne delegation in combat search and rescue mission. Today's architecture for multi-operator system is based on the centralization of control. And so, in fact, there's one commander giving orders to the tactical level alongside with small units of information. What we aim is to share the control to gain flexibility on operations. As we have observed it, implementing virtual assistant on multi-operators system provides some challenges. And one of the goals for future artificial and virtual assistant is being able to share tasks with other agents. The delegation as this mechanism in operation is established through communication first and sharing situational awareness. To support this type of distributed architecture, it is necessary to set up common spaces through the concept of exchange of relevant knowledge. This is where the Continuums projects comes in. Its objectives is to first enhance the knowledge flow of the operations through system architecture and technologies. Two, the main concept we're exploring is giving the right information to the right operator. And third, using the distributed situation awareness model as a support for knowledge exchange with compatible representation. This approach takes into account that under the concept of agent, there are the human operator, but also the artifacts along them. So the problematics is the following. How can we design a system or future virtual assistant feature to support the sharing of information to allow delegation? And more precisely, we wanted to scale the value of the information to display to each operator for their collaborative task. We think that distributed situation awareness as a model would help us to move towards the mechanism of delegation. To correctly evaluate this process, we have designed a methodology and a sandbox environment to support our current and future problematics. Thanks to the DSA approach, we have defined several concepts around the relevant knowledge exchange and some concepts around the common relevant operational picture, or CROP. This represents, according to this example you have on your right, the following. We have here two agents, the pilot and the controller, and as they're capturing their view, they have this unique point of view that is collected by the sensors and everything that is around them. So this is the personal operational picture. They also have similar events, pilot and controllers seeing the same thing in the radar, and here comes into the common operational picture space. It's the COP. Some studies show that sharing the entire COP to the crew member or the member in a mission can cause information overloading or cause higher workload. So what can be beneficial is to pass through the personal relevant operational picture. So it's the POP, as you saw it, information filtered with the requirement information according to the task of each agent. If they need to work together, they will instantly create a crop. So it's representing all the information shared to complete the collaborative task. And the last step for us to build correctly the crop is adding some information from the personal view to the crop, and we call it collective augmented information. It is essential to understand that the crop is highly dynamic, task and role-oriented. To support our method, we have designed, with the help of famous operators, pilots, controllers, and generals, a complex and highly realistic use case to challenge the crop and the delegation mechanism. To explain it briefly, blue forces on the south are trying to destroy the airfield of the red up north. And our participants are playing the pilot or the two fighter squad, which is the leader, and the controller in the AWACS. There are also several air and ground units that are not shown here, but simulated in our environment. During the scenario, sometime later, after entering the enemy zone, the wingman of the leader pilot is hit. At this moment, all the blue forces are replying the mission to support the wingman down. This begins the combat search and rescue procedure. To improve our robustness of experiment, we have split the scenario into 5 stages you have on your right. The first one is hold and push before entering the enemy zone. Then comes the reflex, is when the wingman pilot is down. Then comes the safe phase, with creating safety environment around the pilot down. Then finally, ground and air threat that is giving some complexity to the blue force to manage. Our method depends on the identification on the shared requirement information in 3-step process. The first one is we have extended the mental impact representation analysis to the collective to extract what is shared as information for each agent. This gives us guidelines and can design and develop our crop display. Then we put 6 pairs of pilots and controllers on an immersive simulation representative of the workstation. You have on your center view. And after each phase, we have collected some hot comments on what they have lived individually and what information displayed are relevant or not. Finally, we have conducted collective self-confrontation methods to capture collective comments on the mission and overall. For this project, we and our team have developed a new custom framework. It's called Continuum Core, and it's here to implement each step of the crop process I've explained before, I'm sorry. From the simulator that are rendering personal view of each agent to the crop information displayed at the end in the respective workstation. Each part of the simulator is providing specific data that are what an agent can see in its environment. Those information are stored into knowledge bases powered by ontologies. To get this prop, we apply relevant knowledge exchange built-in blocks that works as a filter according to the situation or phases of each agent. All the information collected from the Continuum Core framework are displayed onto 2 HMI, one for the pilot and one for the controller. Indeed, they do share some information, but according to the collective method, some are specific to each profile. For that task, they are also supported by a common geographical sense reference system that is showing, as it can be, some elements that can be set in a tactical view. To answer our problematics, we have used the scale of relevance. The scale provides 4 different criteria on the value of information. The first one is relevant information for the task in green, knowing if there's a threat or not in the air for the pilot, for example. The second one is irrelevant information for the task in red. The event component does not need it on some phase of the mission. Then useful information, but not essential or not disturbing the task in blue, such as the status of the team. And finally, some missing information that are relevant in gray, like more details on the asset. Now, we're going to look at one of the examples from the results. Those are the results extracted from the save phases after the wingman is hit. And those are all the overall result, pilots and controller alike. On your right, we have plotted all the main components of information associated to the value of information on the scale of relevance, and the y-axis shows the number of responses. For this phase, for example, the tactical situation with taking immediate action, or the checklist, and if there is a packet status going, are considered for both of them really relevant. In the opposite, events, weather, or in-flight reports seems to be irrelevant to the phase. Some information from the assets component, such as the task, role, in fact, asset role, seems to be missing in the achieving task. And finally, some assets need to be put on the secondary level because they are not that needed at this time. So in conclusion, this work is a first step towards creating a relevant common space of information thanks to the crop approach. It will help us to improve the crop display, but also evaluate the delegation mechanism. This mechanism, we believe, could be managed by future virtual assistant in the defense sector, but also in the civil aviation, especially when it comes to air traffic management, single pilot operation, or drone swarm management. Thank you for your time.